Ever stop to, really think about the forces that shape our world?
I mean, not just gravity, keeping our feet on the ground.
But the invisible push and pull happening, everywhere,
Right.
all the time.
Yeah.
Today, we're taking a deep dive into this awesome world.
Guided by the one and only.
Richard Feynman.
And his lectures on physics.
Absolutely.
Going beyond the surface.
Unpacking what forces actually are,
How they work.
at scales big and small.
And why some are more fundamental than others.
It's about gaining that aha understanding.
Without getting lost in a physics textbook.
Feynman had this knack for asking deceptively simple questions.
That could unravel the deepest mysteries.
Okay.
He never took the obvious for granted.
And that's the spirit we're bringing to this deep dive.
It reminds me of something I learned way back in
High school physics.
Yeah, okay.
Remember that classic equation?
F equals ma.
Sure.
Force equals mass times acceleration.
Seems so neat
Yeah.
and tidy.
It's a great starting point.
Sure. But as Feynman would point out,
Physics thrives on building models of the real world.
and those models
They're
are
always approximations
Right.
for all its elegance.
doesn't quite capture the full picture when it comes to forces.
So it's like a good rule of thumb.
But then reality throws us curveballs.
Exactly.
Think about an airplane for a second.
Okay.
It cuts through the air.
It faces drag.
Right.
Right.
You might think.
Biggie, we can just add that into our equation.
Uh-huh.
But here's where it gets really cool.
Turns out that at high speed,
The drag force isn't just related to acceleration.
it's actually proportional to the square of the airplane's velocity.
Wait, so even a small increase in speed?
Could mean a huge GE jump in drag.
You got it.
And to make things even more interesting,
At very low speeds.
the relationship between drag and velocity changes yet again.
And we haven't even touched on how the shape of the plane itself.
Throws another wrench into the equation.
Suddenly designing an airplane feels less like,
Plugging numbers into a simple equation?
and more like
I don't know.
navigating a minefield of aerodynamic complexities.
And that right there.
Is a perfect example of what we're talking about.
Physics is about finding the most useful approximations of reality.
Not always about chasing perfect equations.
As our understanding of the natural world expands,
These approximations often become more intricate.
not less.
It's a good reminder that science
Is a constantly
evolving journey.
Okay, so if even simple laws like ESMA have their limitations,
What about something like friction?
we all experience it every day.
Friction is a fantastic example.
On the surface, it seems so straightforward.
You push a book across the table,
It encounters resistance.
the end.
Right.
But zoom in to the microscopic level.
And a whole hidden world of complexity opens up.
Okay, you've piqued my curiosity.
What's really happening at that tiny scale?
Picture this.
Two surfaces
Seemingly smooth.
rubbing against each other.
Okay.
But on the atomic level,
They're anything but smooth.
it's more like a jagged,
uneven landscape.
the atoms at those contact points.
They actually cling to each other,
As you push these tiny bonds, stretch and snap,
creating vibrations that dissipate energy.
which we feel is heat,
Wow, so even something as commonplace as friction.
has this incredibly intricate dance happening at the atomic level.
That's amazing.
And just like with our airplane example,
Those seemingly simple laws we use to describe friction,
like the classic friction coefficient
they have their limits too.
approximations.
Always approximations.
You've definitely given me a whole new perspective.
On those everyday objects we take for granted.
So we've got friction,
Their resistance.
the limitations of F,
It feels like forces can be anything but straightforward.
right?
Forces can get really complex.
Especially at the macroscopic level.
But here's the fascinating thing.
There are also forces governed by surprisingly simple,
Even elegant.
laws.
Okay.
We call these...
Fundamental forces.
Okay, this is where it gets really intriguing.
Fundamental forces.
What makes them so special?
Tell me more.
Fundamental forces are like the bedrock of particle interactions in the universe. Like, they're the forces that, as far as we can tell, can't be explained by anything more basic.
So they're like the ultimate rule breakers or maybe rule
This
makers?
is already blowing my mind.
But what are these fundamental forces?
I need to know more.
Well, two that you're probably already familiar with are gravity.
And the electric force.
Oh, okay. Those ring a bell.
But remind me what makes them so fundamental.
Compared to, say, the friction we were just talking about.
Here's the fascinating thing about these forces.
Even though we see their effects everywhere,
From planets orbiting stars to the static cling in your laundry.
the laws governing them are incredibly simple.
Okay.
Both gravity and the electric force follow something.
Called the inverse square law.
Inverse square law.
Now there's a term I haven't heard in a while.
Feel like I'm back in physics class, but in a good way.
It's really quite elegant when you think about it.
The strength of these forces decreases with the square of the distance.
Between objects.
Okay.
So if you double the
The
distance,
force becomes 4 times weaker,
triple the distance, 9 times weaker.
and so on.
It's all coming back to me now.
So no matter how complex the objects are or how far apart,
These fundamental forces always behave in this predictable, elegant way.
precisely, and that's the beauty of it.
This inherent simplicity
Even as our understanding of the universe gets more complex.
is what makes them fundamental.
That's mind-blowing.
Okay, so we've got gravity, the electric force,
Are there any other fundamental forces?
governing the universe.
There are actually 2 more. The strong and weak nuclear forces.
But those are definitely a topic for another deep dive.
They're all about the interactions happening within the nucleus of an atom.
At a scale that's almost unimaginably small.
Okay, adding nuclear forces to my list of future deep dives right now.
But for now,
Let's stick with gravity and the electric force.
while we can still kind of wrap our heads around them,
To really grasp these forces, it helps to think about them in terms of something called
fields,
fields.
like magnetic fields around a magnet.
You're on the right track.
Fields are essentially a way to visualize how forces can act over a distance.
Even when there's nothing physically connecting the objects involved.
Okay, I'm intrigued.
But I need a bit more help wrapping my head around this whole field concept.
That is a play to say.
Those electric forces we were just talking about.
Imagine a single electron just hanging out in space.
Okay.
Now, this electron has an electric field surrounding it.
Even if there's absolutely nothing else nearby,
So it's like an invisible aura surrounding the electron.
influencing its surroundings.
That's a great way to put it.
Now, if you bring another charged particle close by,
This second particle will feel the electric field created by the first electron.
and depending on whether that second particle is positively or negatively charged,
It will either be attracted to or repelled by that first electron, right?
opposites attract and all that,
Exactly. The electric field acts as a kind of mediator for the force.
influencing how those charged particles interact.
And here's where it gets really interesting.
Fields aren't just some mathematical trick we use to describe these forces.
They actually carry energy and momentum, just like physical objects.
Whoa, so they're more than just a way for physicists to visualize forces.
They have their own reality in a way.
Precisely, think of it like this.
If you wiggle an electron,
It creates a disturbance in its electric field.
and that disturbance travels outward like ripples spreading out from a stone,
Thrown into a pond
so it's almost as if the field has a memory,
of what that electron did.
even if it's no longer in the same spot.
In a sense, yes.
That's how the universe keeps track of these interactions
Even as things get incredibly complex with particles constantly moving around.
and interacting.
That is so cool.
I never would have thought about fields that way.
Okay, so we've got these fundamental forces
And we've got fields with a memory.
influencing how objects interact across space.
What else did Feynman have up his sleeve?
When it came to understanding the wild world of forces,
Well, he also dives into this really intriguing concept.
called pseudo forces.
Pseudo forces.
Okay, now you've really piqued my curiosity.
That almost sounds like something out of Star Wars.
What in the world is a pseudo force?
It's a force that appears to exist because of the way we're observing a system.
Not because of any fundamental interaction like the forces we've been discussing.
Okay, now you're just messing with me, right?
How can a force seem real, but not actually be real?
It all comes down to your frame of reference.
Imagine you're in a car that suddenly accelerates forward.
Okay.
You feel yourself pushed back into your seat, right?
Yeah, we've all been there.
Now, from your perspective inside the car,
It feels like a force is pushing you backward.
but someone standing on the sidewalk would see that there's no actual force involved.
Your body's just trying to resist the change in motion.
But to you, it feels like a force.
Okay, that makes sense.
It's all about perspective.
So that feeling of being pushed back in my seat.
That's a pseudo force.
Exactly. It's not a fundamental force like gravity or electromagnetism.
It's just a consequence of being in an accelerating frame of reference.
Mind officially blown.
Okay, so we've covered forces from different scales.
But pseudo forces are something else entirely.
They're forces that arise from how we observe things.
What other strange and wonderful examples of pseudo forces?
Did Feynman talk about in his lectures?
I am ready for more.
Picture this, a jar of water sitting calmly on a table.
Okay.
Now imagine pushing that jar with a constant acceleration.
What do you think happens to the water level?
Okay, let me visualize this.
We've got the water at rest.
Then the jar starts moving.
I'm going to guess the water level tilts.
With the higher side at the back of the jar.
Like it's trying to stay put.
You're spot on.
It's as if the water wants to play catch-up.
Resisting that change in motion?
Right. Because of inertia.
The water wants to keep doing its own thing,
Yeah, exactly.
and that's where the pseudo force comes in.
From the perspective of the water inside the jar,
It's as if some mysterious force is pushing it backward.
causing that tilt,
That's so bizarre when you really think about it.
even though we know it's just inertia at play.
It's almost easier to picture it as an actual force acting on the water.
It's a really helpful way to visualize what's going on.
And this leads to a truly mind-bending question that Feynman posed.
Okay.
What if gravity itself
Is just a really big pseudo force.
hold on gravity
As in the force that keeps our feet on the ground.
keeps the planets in orbit?
You're saying that could be a pseudo force too.
Now it is a fundamental force.
But stick with me here.
Imagine for a moment that instead of being pulled down by gravity, we're actually constantly accelerating upward.
In a humongous universe-sized elevator.
Okay, I'm trying to wrap my head around this.
It's like we're all on a cosmic amusement park ride.
Constantly going up.
And wouldn't that upward acceleration feel exactly the same?
As the downward pull of gravity?
You're right.
It probably would feel the same.
But if we're always accelerating upward,
Wouldn't we eventually hit?
I don't know, the ceiling of the universe or something.
That's where things get really interesting.
Einstein's theory of general relativity essentially says that space-time itself,
Isn't flat like we tend to imagine it?
it's actually curved in what we experience as gravity.
Is just a consequence of us moving along these curved paths.
Okay, now we're getting into some seriously complex territory.
Curved space-time.
That sounds more like science fiction than anything else.
It definitely has a mind-bending quality to it.
To be honest, the math behind it can get really intense.
But the main takeaway here is that Feynman loved to use thought experiments like this.
To challenge our assumptions about even the most fundamental concepts.
And gravity is about as fundamental as it gets.
I'm definitely starting to understand that about Feynman.
He really seemed to enjoy poking at the edges of what we thought we knew.
So we've explored the world of forces from so many angles today.
From everyday friction and air resistance.
To those mind-bending concepts of fields and pseudo-forces.
Even touching upon the mysteries of nuclear forces and the curvature of space-time.
It's quite a testament to Feynman's genius, that he can make even the most complex ideas.
In physics, feel engaging and spark that sense of wonder.
He truly had a gift for making physics come alive, didn't he?
It makes you want to grab his lectures and just dive right in.
So as we wrap up this incredible deep dive,
That's one final thought-provoking question our listeners can take away with them.
how about this? If we could truly understand and control all the fundamental forces,
At play in the universe.
what would we be capable of achieving?
It's a question that pushes the boundaries of science fiction.
But it's grounded in the very real laws of physics that we've been exploring today.
That's a question that will definitely keep me pondering for a long time.
And on that note, a huge thank you to our amazing expert for joining us.
On this deep dive into the world of forces.
And to our listeners, keep that curiosity alive. Keep asking those big questions.
And we'll catch you on the next deep dive.